Hey everyone, and welcome back to the channel. Today, we're diving into a fascinating paper that could change how robots learn to move. Imagine trying to teach a robot to pick up a cup, but it's never really understood how to move its arm smoothly. Sounds tricky, right? Absolutely, Jenny. That's exactly the core problem this paper, Learning Action Priors for Cross-embodiment Robot Manipulation, addresses. They propose a clever two-stage approach. First, teach the robot the fundamental grammar of motion, almost like a blindfolded apprentice practicing basic movements. Only then do you teach it to see and understand what it's supposed to do. So, what's wrong with how robots learn now? Don't they just watch us and figure it out? That's the common approach, Jenny, using what are called Vision Language Action, or VLA, models. They're built on powerful visual language models that understand what things are and what words mean. But here's the catch: the part of the model that actually generates the robot's physical movements, the action module, usually starts from scratch. It's like asking a chef to learn how to chop vegetables, cook a gourmet meal, and understand the recipe all at the same time. It's incredibly inefficient and often leads to jerky, unstable movements, especially when you try to apply it to different types of robots. Okay, so the action module is the weak link. How does this paper's two-stage framework solve that? The core idea is brilliant in its simplicity. In stage 1, the robot's action module only learns to move. It's given raw action trajectories, just sequences of joint movements, without any visual input or language instructions. Think of it as a robot practicing Tai Chi in a dark room, focusing purely on smooth, coordinated motion. Once it masters these basic movements and understands the structure of physical actions, then in stage 2, this pre-trained action module is integrated into the full VLA model. Now, the robot learns to perceive the scene and follow instructions, but it already knows how to move plausibly. That makes so much sense. So, what kind of action module are they using to learn these motion priors in stage 1? Is it just memorizing movements? Not at all. They use a sophisticated encoder-decoder architecture, similar to what you might see in language models, but adapted for actions. The encoder takes a whole chunk of robot actions and compresses it into a compact, latent embedding. This embedding isn't just a list of numbers, it captures the meaning of the motion, like grasping or translating, over time. Then, the decoder uses this embedding to reconstruct the original action chunk. They use something called flow matching for this, which is great for modeling continuous, complex action distributions. It's about understanding the dynamics of motion, not just individual points. Okay, so stage 1 creates the smart action module. How do they then transfer that knowledge to the VLA model in stage 2 without messing things up? Great question. They do it in 3 clever ways. First, they simply reuse the pre-trained decoder from stage 1 as the VLA model's action head. It already knows how to generate plausible movements. Second, they use latent alignment distillation. The stage 1 encoder acts like a teacher, providing a structured target for the VLA model's predicted action features, guiding it into the learned motion space. This is crucial early on, then it gradually fades out. And third, the stage 1 encoder also becomes a history compressor. It takes past state action sequences and boils them down into a single context token, giving the VLA model a memory of what the robot has done, which is super helpful for long, complex tasks. This sounds incredibly effective in theory. What did the experiments show? Did it actually make robots move better? The results are really compelling, Jenny. They tested it across 13 diverse robot manipulation tasks, both in simulation and on a real Franca robot arm. The model with action priors showed significantly faster convergence during training and achieved higher success rates across the board. Crucially, it performed much better on data-scarce, real-world tasks, where other methods struggled. For example, on a grasped Coke task, success rates jumped from 5% to 35% just by adding the action prior. And with history compression, it went up to 50%. It truly makes the robot's movements more stable and decisive. Wow, those are some serious improvements. Can we actually see the difference in how the robots move? And are there any limitations to this approach? Absolutely. Figure 4 in the paper shows a striking qualitative comparison. Without the action prior, the robot often moves jerkily, hesitates, or gets stuck. With the action prior, especially with history compression, movements become fluid, precise, and decisive. For example, in a stack cups task, the prior-enabled robot lifts the cup high enough and moves smoothly, while the baseline collides. However, the authors do note that the amount of action-only data used in stage 1 is still modest, and there's a trade-off in how long the distillation process should last. Too long, and it can over-constrain the VLM. So, this paper really highlights the importance of teaching robots the fundamentals of movement before throwing complex visual and language tasks at them. What's next for this research? Exactly, Jenny. The key takeaway is that providing a structured action prior significantly stabilizes and accelerates VLA training, especially for diverse robot embodiments and data-scarce scenarios. The authors believe that scaling up the action-only data in stage 1 could lead to even more generalizable motion priors, further boosting downstream performance. This framework offers a clear path towards building more robust and versatile generalist robots that can adapt to new tasks and environments with greater ease.